Thanks to Jill. Again, I'm Maysam. I came from Concordia University, and this work is done under co-supervision of Dr. Lingyu Wang and Dr. Hong. So I would like to first present a highlight of the work. In this work, we present an approach called multi-view, and our goal is to reduce the information leakage, and we achieve information leakage reduction down to 1% of the state of the art. We could preserve the utility, the same level as the state of the art, and we also achieve a minimization of communication overhead, the same as the state of the art. And we achieve all these three angles at the cost of more computation cost, which is increasingly cheaper nowadays, considering cloud applications. So I would like to start with some introduction of the work, following up with some backgrounds. Then I will delve into the multi-view approach. I will provide two schemes, and then I will present the experiments and our findings with under our approach, and then I conclude the talk. So first of all, network traces, outsourcing network traces is a crucial and demanding task, considering the monitoring task, which is going to be more sophisticated, and the need for outsourcing them for to managed security service providers called MSSPs to take the job efficiently and with experienced analysts. However, organizations are typically reluctant to outsource their network traces due to privacy concerns, mainly from both sides, user and client of the organizations, and also from organization's perspective. From the to be more specific, from the customers, their personal activities could be leaked and targeting them with ads and blackmailing, while topology of the network of the organization can also be leaked and resulting in weakening the whole network topology. And lastly, according to GDPR Article 28, ISPs cannot share tenants' data without required protection. So in cases when ISPs and the network providers are convinced to share their network traces, the trace is typically subjected to some anonymization functions. This anonymization function should comply to two different requirements, mainly from ISP point of view and analyst point of view. From ISP perspective, the data owner needs to be convinced that the data is protected enough. And from the analyst perspective, the anonymized data should be accurate enough to enable different and various types of analysis. One of the well-known anonymization function, which is recently introduced, not recently, actually, it's 2002, published in ICNP, is called CryptoPAN, which is a cryptographic prefix preserving IP anonymization, which from now in the talk we called it as PP. It gets a key and it encrypts the IP and outputs completely different IPs. Such that if two IPs sharing X bits, the output also share X bits. However, this utility-driven anonymization function is known to be vulnerable to a variety of semantic attacks, which is including fingerprinting, injection attack, structure recognition, so on and so forth. Now I'm going to present very briefly one of those attacks called injection. In this attack, the adversary will insert some forged packet inside the original trace with the goal of identifying and recognizing this forged packet through the CryptoPAN output. So using some strange source port or even some pattern inside the injection. So he or she identifies the inserted packets. Then he tries to identifies more flows by just checking the matches of prefixes. So from originally 159, which he or she already injected, he find the other two IPs from the same subnet, but from other customers or even the network providers. And at the end of the day, you could de-anonymize the trace partially or fully, depending on how much injection he has done. So to put this in a nutshell, and to summarize this existing work against semantic attack, all the existing work, there are a variety of network anonymization tool that is provided, and each of them is working with different fields of the network, and they have built around different type of anonymization methods. However, to have a good comparison between these algorithm and these methods, most of these solutions are vulnerable to those semantic attacks, and those that are not vulnerable, they sacrifice a lot of utility of the network, which is completely rendering the usefulness of the data. So now it seems that again we deal with the same famous privacy utility trade-off, and we thought about this. We asked ourselves this question actually: can we have the best of both worlds by sacrificing something else, something more expendable? And we get to this answer: what if we preserve both sides, privacy and utility, with more computation, which is nowadays cheaper and cheaper, especially with cloud. So the trade-off, the two-way trade-off, is going to be a triangle between computation, utility, and privacy. Before delving to the solution, I would like to first present briefly the adversary model I assumed based on those semantic attacks. So in very aligned to the state of the art, our adversary is honest but curious in a sense that he would follow he or she will exactly follow our approach, and the adversary can also observe the anonymized trace. The goal of the adversary is to find all possible matches between anonymized trace and the original trace. And suppose that the whole trace includes D groups of IP, in which these D groups could be delimitarized or delimitarized zone like subnets. We assume that the adversary has alpha knowledge, which means that he already injected or fingerprinted alpha of those subnets. We call this adversary knowledge alpha knowledge from now on. So basically, our multi-view approach in a nutshell is to generate multiple views from one view called seed view to preserve both privacy and utility, such that the real view, which is a utility-driven view, is hidden among many fake views. In this way, privacy will be preserved, and utility will be preserved by secretly retrieving the analysis corresponding to the real view. However, there's a key challenge: how to minimize the communication overhead, considering the sheer size of network traces, which could go like beyond billions of records. We propose this solution that, okay, as a data owner, we send one seed trace to the data analyst, and the data analyst generate multiple views out of this seed trace. In this way, the communication overhead could be completely removed. So in a very high-level multi-view approach works like this. We have two players, data owner and data analyst. And the data owner, using a block called seed trace generator function, generates a seed trace which is not prefix preserving anymore and does not leak, is not subjected to that semantic attack. This seed trace, together with some supplementary parameters, is going to be outsourced to data analyst, where the data analyst, using those parameters and the seed trace, can generate multiple views out of the seed trace. And he does he or she does analysis on each of those views. And finally, the data owner retrieve the result corresponding to the real view. To be more specific, again, let's assume this is original trace. In step one, the original trace goes under a partitioning algorithm, which I will explain on this in the forthcoming slides. This partition trace goes under CryptoPAN, the prefix preserving function, which I already introduced, with different number of enumeration for each of the partition. So, for example, for partition number 1, we encrypted 1 time. For partition number 2, we encrypted 3 times. In this case, by doing so, the seed trace is not prefix preserving in its entirety. As you see, the logos of the partition is completely different than the original one. This locally prefix preserved version of the original trace is then sent to the analyst, and the analyst, using the key and some supplementary parameters, is able to generate the 3 views, in which one of the views, the green one, is corresponding to the real view. Finally, he does the analysis, and ORAM is going to be used for retrieving the real data. However, the benefit we get from this multi-view approach is we minimize the communication overhead without any increasing of the size of the trace. We can preserve privacy by hiding one view among others, and we preserve the utility by secretly retrieving the results. Now, getting back to, so we are now sure about communication overhead and utility of the trace. But what about the privacy? How much privacy is going to be improved? So the first question that comes over here is, okay, you generate multiple views. You have to make sure that our alpha knowledge adversary cannot distinguish it among the fake views. So we propose this definition, which is inspired by differential privacy, and we assume that the fraction of probability of view I may be the real view over the view R, which is the actual real view, be the real view, should be bounded. And we call it as epsilon indistinguishable multi-view approach. So the less epsilon you have, the better indistinguishability. For example, in case of epsilon 0, all the views are completely indistinguishable from the alpha knowledge adversary perspective. However, before proposing this multi-view mechanism, I would like to first introduce one vulnerability of multi-view, mainly inherited from CryptoPAN collision resistancy. So because CryptoPAN is a cryptographic protocol based on Rindal block, it's collision resistance. So if you encrypt 2 IPs sharing prefixes, but with different number of enumeration, the result is not gonna be prefix preserved anymore. So for example, here in original trace, we have 2 IPs 150 sharing 150.10 as a subnet, but in the fake views, that the IPs goes under different number of CryptoPAN encryption. For example, partition 1 4 times, partition 2 3 times. We will not see any shared prefixes, and it is only in the real view that both of them are encrypted equally that the shared prefixes will emerge. So without any adversary knowledge, just using this vulnerability that is inherited from collision resistancy, adversary can identify the real view. To solving this, we introduce IP collision into CryptoPAN so that whenever adversary sees a shared prefixes, he cannot contribute it to the real or fake view. It could be a fake shared prefixes or a real shared prefixes. And the solution is we completely remove the prefix of the IPs, and we use PP to separate them back to their subnet. So for example, 150.10 and 150.10 that shared prefixes, they goes under CryptoPAN 1 time, while 128, which is not under that subnet, it goes to CryptoPAN 2 times. So from now on, shared prefixes is just showing up using the indices. If the indices are equal, indices of the CryptoPAN is equal, for which indices is the number of times that CryptoPAN is applying, then the 2 IPs are inside the same subnet. And if it's not, so they're not. So that's why in fake view, we can see the first and the third IP shared prefixes, while they originally do not have any shared prefixes. So after resolving this problem, now I would like to present the epsilon distinguishable multi-view mechanism that we propose in the paper. We propose 2 schemes. The first one achieves the perfect indistinguishability, epsilon 0. However, each of the views is subjected to huge amount of leakage. So without caring about which view is the real view, by just looking at the fake views, a lot of leakage could take place by the adversary. In this scheme 2, we sacrifice some of the indistinguishability in the sense that a few number of real view is going to be discarded, but we still remain with a lot of real view candidates to achieve better protected partitions. So I would briefly explain scheme 1. In scheme 1, basically IP, all the IPs sharing prefixes are gonna be clustered in one partition, and then each partition goes under CryptoPAN and encryption. But to explain this more precisely, the data owner first generates a random vector corresponding to the number of partitions. In this case, we have 2 partitions, so the random vector is gonna be a vector of 2 with completely random numbers. So it's gonna be 1 and 2, for example. Then he fixed the index of the view that he wants to be the real view. For example, he wants to be the third view to be the real view out of, let's say, the 10 view that he requests. Then the data owner calculates V0 as minus time RV, which is gonna be -3 and -6. So here he encrypts the first partition -3 times and the second partition -6 times. Here minus means reverse CryptoPAN, and we introduced this in the paper, and it's one of my backup slides if you have any question about that. So partition 1 is 3 times reverse CryptoPAN, partition 2 is 6 times CryptoPAN, and after 3 times applying this random vector doesn't leak any information, he will get back to the real view without even knowing this. However, the problem of this scheme is each of these partition carries a lot of information, which is everyone knows that the partition includes IPs sharing prefixes, and I will show you the information leakage for this scheme. In the second scheme, which due to time I have to skip it, it's like the data owner, instead of sending just one key vector, he sends n key vectors to generate all the n views, and each of these key vectors are designed somehow that we achieve a certain level of epsilon indistinguishability. So the indistinguishability analysis for this scheme 2, I will explain it briefly in next slide. But basically the idea is the distinct IPs are gonna be mixed or migrated back together using these key vectors. So in scheme 2, we realize that by some combinatorial calculation, that the indistinguishability parameter epsilon of scheme 2 is lower bounded by this formula, which is a relationship between number of distinct addresses, number of prefix group, and adversary knowledge. And the more number of prefix group we have, which means the more network is scattered, the better epsilon indistinguishability will get. Now, let's see the experiments. So, for the experiment, our data set was a 70 gig of real ISP data set, which includes 883 distinct IP addresses, and our experiment was conducted based on 1 million packets. So this graphs basically shows how epsilon indistinguishability works if we group IPs based on first octet, which is 136 groups. If we group IPs based on first and second octet, which is 417, and if we group them based on the first 3. So you see, as our calculation here predicted, in the third class of experiment, we get a better indistinguishability. In terms of computation overhead, we realize that even in the worst case, which is the 3-octet grouping, we go to less than 200 seconds for 160 views. And this is the schema, this is the graph comparing both schemes, which shows that scheme 2 is pretty much close to the CryptoPAN, which is our baseline in terms of leakage, while scheme 1 can completely reduce the information leakage using the number of views that you generate. So for privacy evaluation, in the paper we have the privacy up to 100%, but in the slides I just presented for up to 50% of the prefixes that is plotted. So here, this is the first case when we have 137 groups. As you see, the black one is the CryptoPAN results, and the dashed line is for the multi-view. And in the best case, we get less than 1% compared with 50%. Not 1%, less than 5% compared with 50% of leakage for CryptoPAN. And this graph is corresponding for this graph, which is showing the number of real view candidates. So, for example, when we have 50% adversary knowledge, basically adversary is able to discard all the views except something around 20 views. But still with that 20 views, we get a leakage much better than the CryptoPAN. And this is when we group them based on the first and second octet, which the real view candidates number is improved, and correspondingly the leakage too. What else I wanted to say here is, yes, the attack we used here is frequency analysis, which is after discarding the non-real view candidate, the fake views, we apply the frequency analysis on the each of the trace, and we run the experiment 1,000 times, and we make an average. That's how the graph is actually produced. Finally, this is the experiments for the utility evaluation. I don't know if I have.
You're running.
Okay. So if this is the case for the utility, it's pretty much the same as CryptoPAN. It's not something more. Just as a conclusion, if you see this graph, this is where all the clustering groups and perturbation-based solution are located, which is basically privacy but without utility. CryptoPAN is over here. Good utility but no privacy against semantic attack. And very graphically, multi-view can just preserve both. And we achieve this by trading off utility and privacy with computation cost. Thank you. Any questions?
So it seems that you assume that the attacker has knowledge of some very specific pairs of matches between the real trace, in the real trace. However, if you actually reveal the full real trace, isn't there a lot of additional information that is just publicly available that you could use?
We model all those. It's not about the pair. It's about what number of prefixes or subnets the adversary has knowledge of. It's not about the pair. So it's like how many of those prefixes is originally, let's say, polluted by the adversary. And that all those public information which comes from DNS queries or injection, we model them as alpha knowledge attacker, which means he has knowledge of alpha of the different types of IPs. And because CryptoPAN is prefix preserving, he can use them in de-anonymizing the trace.
So maybe a very quick question. You mentioned you work with honest but curious adversary. Mm-hmm. So is it kind of a reasonable assumption? And what would you be able to do for a stronger adversary model?
The stronger could be dishonest, right? The one who just not follows our solution. But in that sense, privacy is not going to be damaged. Just the integrity of the solution will be damaged. But we didn't consider integrity in this problem. We just wanted to study the privacy and utility to be preserved using computation cost.
Okay, thanks a lot.
Thank you.